Just like forward differences, we can have backward differences also. Let y equal to f of x be a function which gives the values y0, y1, y2, etc. up to yn, corresponding to the equally spaced x values x0, x1, x2, etc. xn. The interval of differencing being h. Then the first backward differences of the function y equal to f of x are f of x0 plus h minus f of x0, f of x0 plus 2h minus f of x0 plus h, etc. f of x0 plus nh minus f of x0 plus n minus 1 h, or this f of x0 plus h is y1, f of x0 is y0, so this is y1 minus y0, this is y2 minus y1, etc. The last term is yn minus yn minus 1. For simplicity, we may write this as nabla y1, nabla y2, nabla y3, etc. nabla yn. The symbol nabla is called the backward difference operator. So, nabla y1 equal to y1 minus y0, nabla y2 equal to y2 minus y1, nabla y3 equal to y3 minus y2, etc. nabla yn equal to yn minus yn minus 1. If you look closely, you can see that this nabla y1 is nothing but delta y0, and nabla y2, which is y2 minus y1, is delta y1, and this is delta y2, etc. Nabla yn equal to delta yn minus 1. Like forward difference tables, we can create backward difference tables also. Let's make one backward difference table. Assume that we have a function y equal to f of x, and it assumes the values y0, y1, y2, y3 and y4 corresponding to the x values x0, x1, x2, x3 and x4 respectively. So we may write the table as x and y in the first two columns, x0, x1, x2, x3 and x4. The corresponding y values are y0, y1, y2, y3 and y4. The first differences are represented by nabla y. The first difference that we can form is between y1 and y0. It is y1 minus y0 is nabla y1. Then y2 minus y1 equal to nabla y2. y3 minus y2 is nabla y3. y4 minus y3 is nabla y4. The second backward differences are nabla square y, of which the first one is nabla y2 minus nabla y1, which is nabla square y2. Then nabla y3 minus nabla y2 equal to nabla square y3, and finally we have nabla y4 minus nabla y3 equal to nabla square y4. The third backward differences, nabla square y3 minus nabla square y2 is nabla cube y3, and there is one more, nabla square y4 minus nabla square y3, which will give you nabla cube y4. Finally, the fourth backward difference is nabla cube y4 minus nabla cube y3, which is nabla raised to 4 y4. We may redraw the table in a simple way. Here we have written the x and the corresponding y values. Different columns are assigned for the first, second, third and fourth backward differences. The first backward differences are written in the third column. Nabla y1, nabla y2, nabla y3 and nabla y4. In the fourth column, the second backward differences. Nabla y2, nabla square y2, nabla square y3 and nabla square y4. In the next column we will have the third backward differences as nabla cube y3 and nabla cube y4. Finally we have the fourth backward difference as nabla raised to 4 y4. We can see that the backward differences of a given y value lie along a diagonal with an upward sloping. For example, take the case of y4. The backward differences for y4 are lying along this diagonal. Or take y3. The backward differences are lying along this diagonal with this positive slope. Or for y2 or y1. There is an alternative notation for these backward differences. It's like this. Say nabla f of x equal to f of x minus f of x minus h. Then nabla f of x plus h equal to f of x plus h minus f of x. This we know as delta f of x. Say nabla f of x plus 2h will be f of x plus 2h minus f of x plus h, which is nothing but delta f of x plus h. Likewise, proceeding in this way, we can write nabla f of x plus nh equal to f of x plus nh minus f of x plus n minus 1 h, which is delta f of x plus n minus 1 h. Similarly, we may write nabla square f of x plus 2h as nabla of nabla f of x plus 2h. But nabla f of x plus 2h is delta f of x plus h. So this becomes delta f of x plus h. It is operated by nabla function. We interchange these notations and rewrite it as delta of nabla f of x plus h. But nabla f of x plus h is delta f of x. So this is equal to delta into delta f of x, or this is equal to delta square f of x. Following the same procedure, we can write a general equation for this as nabla raised to n f of x plus nh equal to delta raised to n f of x. Now we shall find a relationship between the backward difference operator and the shift operator, E and nabla. We know that nabla f of x equal to f of x minus f of x minus h. This could be written as f of x minus e raised to minus 1 f of x. Nabla is equivalent to 1 minus e raised to minus 1, or nabla equal to 1 minus 1 by e equal to E minus 1 by E, or nabla equal to E minus 1 by E. This is the relationship between nabla and the shift operator E.